Alright guys, back here again. Sorry you have to see my ugly face, but at least I put a button-down shirt on this time. Put some basic information over here on the left. We've got just our first problem in the week 3 calculations over here on the right. We'll kind of work through these. You're going to need your calculator again. Just the basic information. We've got inverse square law formula. Always going to need that. Decaying source or half-life here, and then dose equals dose rate times time. Okay, inverse square law, you guys dealt a little bit with this last week or in the week 2 calculations. The decaying source here you guys dealt with in the week 2 calculations as well. And this just looks familiar, just missing a couple of numbers here. Let's say we had 100 curies of iridium-192. We wanted to figure out how many curies we had today. Let's say we just had 100 days old just for kicks and grins here. 100 curies divided by 2 to the power of 100 days divided by our 75-day half-life up here. Just normal stuff there. Okay? That's going to get us down to how many curies we had now, and then if we wanted to convert that to Rankins, we would multiply that remaining number times 5.2. Okay? If it was cobalt, we would use 14 down here and some other things, but we would have to remember that that guy is in years. So, let's jump over here to the right-hand side. Like I said, this is problem number 1 out of your week 3 information. So we're going to say 50 curies of iridium. We have it exposed for half an hour. Where are the 2 and 5 MR per hour boundaries? Okay? So just for fun here, let's just say this. First time you actually get a little picture. It's not going to be the prettiest, but it'll work. We're looking for a 5 MR and a 2 MR. Okay? We know that when we go from here, 50 curies to Rankins, it's going to be actually in Rankins, or our source strength will be in Rankins. So we need to convert this to millirankins, and we can do that by multiplying by 1,000. So, well, let's just do that. We've got a 50 curie source. We don't have any time. So, using this picture here, we've got 50 curies of iridium. We want to know distance and distance. So, 50 times 5.2 is going to equal something. Okay? Grab your handy dandy little calculator and you can do this with me. 50 times 5.2. That brings us to about 260, and that is Rankins. Okay? But it's not only Rankins, it's Rankins per hour at 1 foot. Remember this guy from last week. So, 260 Rankins per hour at 1 foot here. That tells us 50 curies of iridium standing 1 foot away gives us 260 rem per hour, which we already know that 5 rem per year is the national or the NRC recognized standard. So we're way over that, so you want to be way far away from that. So, little time factor here, half an hour. Okay, we jump back to this guy over here, dose equals dose rate times time. We could do that. I'm just going to get rid of the Rankins per hour right now. Okay, we could say either divided by 2 or times 0.5, either way. Just for now, I'm going to say divided by 2. So divided by 2, that equals 130, because now we've got 130 Rankins per hour. I realize it's only half an hour, but still Rankins per hour. So 50 curies gives us 260 rem. It's only going to be exposed for half an hour, so really we're only going to get 130 Rankins per hour at 1 foot. Now we need to know where the 2 and 5 MR boundaries are. So we're going to take this value and plug it into our inverse square law calculation by this. We know our intensity 1 of 130 Rankine per hour. Okay? We don't know, or sorry, we do know the intensity 2. It's going to be 2 and 5 MR, except we can only work one at a time. So we're going to put this here. Okay? But notice we've got a Rankine and a millirankine. So we need to convert this Rankine to millirankine. We'll do that in a second. We have a distance 1 and we don't have a distance 2. So this is going to be distance 2 squared or x squared, either way. And our distance 1 is always 1 foot squared unless otherwise specified. So we need to get this to millirankine, and then we're looking for that value right there. So in order to get 130 Rankine to millirankine, we just take that times 1,000. So new calculation is going to look like this. 130,000 over 2 millirankine equals x squared over 1 squared. So 130,000 divided by 2, 65,000. And I did that just to do this. because we'd go 130,000 times 1 squared, it's itself, divided by 2, 65,000. Okay? We're left with an x squared. Algebra tells us if you do one thing to one side, you got to do it to the other. So we want x by itself, square root, square root. So square root of 65,000 is 254.95 feet. Okay? That is that value right there. 2 MR, 2 MR, 2 MR. Okay? So now we need to know this value. But first, this tells us if we have 50 curies of iridium, it's going to take 255 feet, roughly, to get out to a 2 MR boundary. That just means that if we were out in an open field, no concrete, no lead, no anything around us, source right here, we'd have to walk 255 feet down there, carrying our survey meter. That would eventually drop down to 2 MR per hour in that one area, and that's only for a half hour. So you can imagine, if we had a full hour, you'd have to go double this distance, roughly 500 feet. Okay? So now, since we know the 2 MR boundary, we're just changing this number here to 5. So we take this value here, because that's what we actually got to, 130,000 divided by 5 now instead of 2, and that's going to equal x squared over 1 squared. So 130,000 times 1 squared, itself, divided by 5. That is 26,000. Okay? Square root both sides. So second square root on my calculator. Oops, that's messed up. Second square root. There we go. That tells us it's about 161 feet, roughly. Okay? So this value now goes right there. So you can see, just by kind of common sense here, this guy back here says if we're going to double the distance, we're going to decrease the dose by a factor of 4. Okay? So we're going from a 5 MR to a 2 MR. So we're only cutting the dose in half. Okay? So we're not quite in half, but we're close there. So kind of take that relationship for what it's worth. Alright? That's that guy. Pretty simple. That's just a little bit of inverse square law and how that works. Okay? Let that soak in for just a second here. So I imagine you're writing furiously. Alright. So now, that's a distance problem. Instead of finding boundaries, and this doesn't matter, 500, 200 MR boundaries, you just plug that number in to the bottom of the inverse square law. Okay? So I'm going to get rid of that, and I'm going to say, just for fun here, we're going to go to collimators. Okay, I know I'm kind of jumping ahead in your work problems, but you'll see them. They kind of go together. Okay, this is number, looks to be about number, oops, got things messed up here. Here we go. Looks to be about number 9 on your sheet. Sorry, no, scratch that. Number 14 it looks to be. It says 86 curies of iridium at 1 foot, 2-inch collimator. We need the second. So, we're going to say, let me just write that down here, 86 curies of iridium. Iridium, 86 curies. And it wants to know Rankine per hour at 1 foot, and then it wants to know Rankines per hour with a 2-inch collimator. So, Rankines per hour collimator. And you'll see what I'm talking about if you scroll down to that question. It also gives us a couple of values here. It says if we're going to use a tungsten a tungsten collimator, the half value thickness is 0.13 inches of tungsten for iridium. So that says this. Every 0.13 inches of tungsten reduces, if we had 100 MR, we had 0.13 inches of tungsten, it would be 50 MR, so on and so forth. So, it's just giving us a value. So we know we're going to use this guy right here. So we need to go 86 curies times 5.2. Okay? Handy dandy little calculators here. that tells us that's 447.2 Rankins per hour at 1 foot. Okay? 86 curies, Rankins per hour at 1 foot. There it is. 447.2 Rankins per hour. Now, we attach a collimator to it. We know that it's 2 inches thick. I should have wrote that up here. 2 inches thick. That's our half value thickness. So we're going to go here. We're going to take this value, 447.2 divided by 2 to the power of 2 inches thick, okay, because we know it's 2 inches, and 0.13 inches is our half value thickness. So 447.2, we're going to divide that by 2 to the power of, open parentheses, 2 divided by 0.13, close parentheses, and we come out with a value of 0.010 Rankins per hour. And that's at 1 foot. Okay? So, nothing too terribly difficult there. That just says, need to figure out what it is at 1 foot. Got it? Okay, we attach a collimator to it. Here it is again. This is just half value layer, half value thickness, half-life, whatever. Plug those numbers in. That's Rankins per hour divided by 2 to the power of is a constant. Our collimator is 2 inches thick. Half value thickness of that collimator is 0.13. So calculate that out, come out to 0.010 Rankins per hour. So that's what would be our final answer. Okay? Again, if you have any questions, just give me a call or email me, either way.